All right. So are there any questions before I start?
Sir,
Yes.
I just want a clarification in the problem set. So
Right.
there was a question regarding sales tax. When a sales tax is levied. So, sir, I actually searched internet and I also saw some websites and some books. Sir, in some books, they move demand curve, not the supply curve, when the sales tax is introduced. But sir, a tutor has done it in a way that he has moved the supply curve, like P minus PT. What I did was I introduced P plus PT in the demand curve only. So how do we know that a sales tax shifts demand curve or supply curve?
So that's, not terribly important. I mean, you can ask for a clarification on the question that, is the tax levied on sellers or on buyers, right? So assume that it's levied on sellers and then you can
Sir,
proceed
in
with that.
general, like the tax is paid by sellers only, right?
Yes. So there's a literal incidence of the tax that, whether buyers have to pay it or sellers have to pay it. So just assume that sellers have to pay it, right? The exact meaning is not important, right? So if there's a tax on sellers, what is the effect? If there's a tax on buyers, what is the effect? So, you could ask for a clarification of the question. So if you get a question, you could always ask that. And if the question says, the question may explicitly tell you, or it may be clarified that, okay, the tax is on sellers, let's say, right? What's important is how to analyze that. Either form of the question, that if it's on sellers, what will be the effects? Is if it's on buyers, what will be the effects? That's what you should try to understand, right? If the question is vague or ambiguous in a problem set, in an exam, you can always ask for a clarification and we'll clarify, right? Is that clear? Okay. Um, so we discussed up to this point about, the last axiom that we made was the axiom of convexity of preferences, which roughly captures the idea that people like a diverse basket of goods, right? It's a preference for diversity. That's the idea that is being captured here. Uh, so let's develop a few notions and then we will move on to discuss the principle of optimal choice by a rational consumer. So one notion is that of indifference curves. And again, from your undergraduate days, most of you would be familiar, but let's, for the sake of completeness, talk about it quickly. So what is an indifference curve? An indifference curve, there may be many indifference curves, right? Every indifference curve has a reference point. So let's say there's a given bundle X0, right? And we can define an indifference curve with respect to X0, and that'll be the collection of all consumption vectors such that the consumer is indifferent between them and X0, right? So the utility of these vectors lying on this indifference curve will all be equal to the utility of the bundle X0, right? So that's the indifference curve passing through X0. And if we chose a different reference point bundle, X1 or X2, we'll have a different indifference curve passing through that. Another way to define or understand an indifference curve is that it's the boundary of the two sets that we were talking about earlier, right? The upper and lower contour sets, or the weakly preferred set and the weakly better set and the weakly worse set, right? It's the intersection of those two sets which gives us the indifference curve. Now, one useful, excuse me, one useful sort of calculus exercise is to derive the slope of an indifference curve, assuming that the utility function is differentiable, right? So an indifference curve is given by this equation, any indifference curve. It's the combinations of X1 and X2 which gives some constant level of utility, right? That's what the equation of an indifference curve is. So if we take that as a starting point and we take total differentials of both sides, right? So suppose x1 and x2 are varied by small amounts of dx1 and dx2. Then what is the total change in the value of the function? First, you have this part, right? This is the partial derivative with respect to x1, or the marginal utility of the first good, times dx1, the amount by which x1 has been changed, plus the marginal utility of good 2 times dx2, the amount by which good 2 has been changed. So that's the total change in the value of the utility if we change x1, x2 by small amounts. And if you have changed x1, x2 by small amounts, but still to stay on the same indifference curve, then the value in this, the total change in the value of the function has to be 0, right? So that's what we get here. And now we can, do, I'm being a little loose here. You can, sort of do this by taking limits and so on with del x1 and del x2. But, skipping the niceties, essentially simple algebra will give us dx2 dx1, which is the slope of the indifference curve at a given point, right? That is given by the ratio, with a minus sign, the ratio of these two marginal utilities, u1 divided by u2. So this is the expression for the slope of uh, uh, an indifference curve. Uh, this is called the marginal rate of substitution, right? What is the interpretation? The interpretation is that if you start at some point in the indifference curve and ask the question, at what rate is the consumer willing to substitute one good for the other, right, for small changes, then this is the answer. Then the slope of the indifference curve captures precisely that. It's the rate at which the consumer is willing to substitute good one for good two, apples for oranges, right? And it's given by the slope of marginal utilities. So keep in mind both the expression we have derived here as well as its interpretation as the marginal rate of substitution. Okay, so what are typical slopes of indifference curves given our assumptions that we have made, the 5 axioms that we have made so far, right? And again, it's not hard to see that, first of all, these indifference curves have to be, they have to be lines, they cannot be bands, right? They cannot have thick portions because if the indifference curves have thick portions, which axiom will be violated?
Local non-satiety.
Monotonicity.
Monotonicity.
Right. Within the band, you can always find a point which contains a little bit more of both the goods, and the consumer is supposed to be indifferent as you move to that point. But how can that be? You're being given a little bit more of both the goods. So that's a violation of monotonicity. Indifference curves have to be downward sloping, right? If they were positively sloped, which assumption will be violated? Again, monotonicity, right? Because then you look at 2 points. One point has more of both goods than the other, but then the consumer is not supposed to be indifferent between them. Also, as you go from a lower indifference curve to a higher indifference curve, that represents a higher level of utility, right? Again, from monotonicity. And finally, the indifference curves have to be convex. Okay. Why is that? That is following straight from the convexity axiom. So let me open up my whiteboard. So suppose our indifference curves were suppose we had concave indifference curves, right? Let's pick any 2 points, A and B. And let's join them by a straight line. Okay, so all these points are weighted averages of the points A and B. Okay, so what does the convexity axiom say? If I pick a point like C over here on this line, my convexity axiom says what? How does the consumer view C relative to A and B?
Averages are
Consumer
preferred.
Averages
Over the
preferred.
averages are
extremes.
preferred over the ends.
Yes. So C has to lie on a higher, so the utility at C should be higher. But look at C, it lies on an indifference curve which is lower, right? So we just discussed the property that as you move upwards or to the right, you should move to higher indifference curves. But here, there's a contradiction of that. As you're moving down, you're reaching a point C where utility is higher, so you're moving to a higher indifference curve in the downward direction, and that contradicts that property. So this can't be true. So the only shape that is possible is the opposite, which is convex, where if you draw a line, a point sitting on that line is supposed to be preferred. And indeed, that is true here because it's lying on a higher indifference curve, right? Also, indifference curves cannot intersect, right? Because if they intersected, again, what assumption will be violated?
Transitivity.
In combination with transitivity, you'll have a violation of monotonicity, right? Because then you can find points like A here and another point like B here, right? Since the two indifference curves, well, so B should give a higher level of utility than A, but then at this point of intersection, so B gives a utility level E1 and A gives a utility level U2. E1 is higher than U2, but then how can the utility at C be both U1 and U2, right? So that's not possible. Okay, so these are familiar properties of indifference curves.
Sir, is the term quasi-convexity only used for utility functions and not to describe, the indifference curves themselves?
The quasi-concavity concept can be applied to any function, right? And I'm glad you stopped me there because I should have talked about a connection before moving on. So any function in principle can be quasi-concave or quasi-convex or concave or convex, right? So that's a general property. Now, given the kind of theory of choice that we are building up, a question to ask is that the various functions that we're talking about, utility function, the indifference curve, which is also a function after all, which of these functions have what property, right? So that's a question. Now, let me write down three statements. So the preference ordering, the preference relationship is convex. That's one possible statement, right? This is indeed the statement of our axiom 5. That's exactly what axiom 5 says, that the preference ordering is convex. Here we are not talking of convexity of a set, convexity of a function. We're talking of convexity of an ordering, right? So it's a very different notion of convexity that we're applying here. A second possible statement is that the function u is quasi-concave. Right? And a third possible statement is the indifference curve is convex. Right? So these three statements are logically equivalent. Each implies the other two and is implied by them. Okay? So again, as I think I mentioned earlier, when you say that something is convex or concave, what is that thing? Is it a function we're talking about? Is it an ordering we're talking about? Is it a set that we're talking about? Indeed, I can expand this list. The same assumption also means that the upper contour set, or the more preferred set, is a convex set, right? So all of these statements are logically equivalent. Yes. We stated our assumption in terms of the preferences because that is our primitive object. That is the thing that we started with. And we wanted to make assumptions on that instead of a utility function or indifference curve, because those are derived objects in this theory, right? We don't start with those. We start with the preference ordering. But it so happens that the moment we insist that the preference ordering has to be convex, it also imparts these properties to the utility function, to the indifference curve, to the more preferred set, and so on and so forth. Okay, now let me move on to the important issue of what is the
So,
principle? Yes,
can I ask a small doubt? Uh,
sure.
when you say that they have to be curves, not bands,
Mhm.
and you say that it is implied by strict monotonicity.
Yes.
Can you explain that again, please?
Okay.
And so, can you please explain a little bit about the concept of quasi concavity also?
Okay. Bands. So let me draw a picture where I'll make the indifference curve a band, right? Um, so the indifference curve or the indifference set, whatever you want to call it. So let's say it looks like this, right? The indifference set is a whole band like this, let's say, right? So what is the problem if this were the case? The problem is that let's pick a point like A, and if it's a band, I can always find another point which contains more of both the goods. So another point B inside that indifference band, such that B contains strictly more of both the goods compared to A, right? But then we are saying that the consumer is indifferent between A and B, these two bundles, even though B has strictly more of both the goods. So that's the violation of monotonicity. Yes?
Yes, sir. Thank you, sir.
Okay. And the other question was, what is quasi-concavity? Okay, so let me go back to a previous slide where I defined it. Um, so this is the definition of quasi-concavity of a function, right? Uh, so this is saying that um, if you take 2 points in the domain of the function, x1 and x2, right? And you evaluate the function at some average of these 2 points, at a third point, which is a weighted average of x1 and x2, right? So that's the inside this function. And you evaluate the function at these two endpoints, x1, x2 itself, right? And take the lower of those two values. So the value of the function at the average will always be greater than the lower of the functional value at these two endpoints, right? Now,
So is indifference curve a function?
indifference curve is a function, yes. I mean,
I'm asking. I'm asking.
the indifference curve uh, can be expressed as some function equal to 0. It's an equation really, right? But it can be written as a function taking the value 0.
Okay, sir.
Right?
Can we say that it's a function where the output always remain constant because the utility is fixed for a particular IC?
Many to one function.
So basically, our indifference curve is given by this sort of an equation. Right? This equation gives us an indifference curve. Now, I can solve this equation and express x2 as a function of x1. Right? And that'll be my indifference curve. Right? So this function will be convex, this g function.
So,
Yeah.
like we said in convexity, averages are preferred over extremes.
Oh.
What does quasi-convexity say about this?
That's what I'm coming to. That's what I was just going to talk about. So here's the formal definition, right? Now, let's see quickly why that is connected to, for example, the indifference curves being convex, right? So our x2 and x1 here. So let's take 2 points, x superscript 1 and x superscript 2. Right? So these are vectors themselves. And suppose they lie on the same indifference curve. So that means u of x1 equals u of x2. Right? And suppose u is quasi-concave, according to the definition that we had on the slides. So that means that if we take some weighted average, and evaluate the utility function there, then it should give us at least as high a value as either of u of x1 or of u of x2, right? So if these are our x superscript 1, x superscript 2, the two vectors, and if the utilities are equal, that means they lie on the same indifference curve, right? That quasi-concavity of the utility function is telling us that if I join this line, these two lie on the same indifference curve. And if I join the line between these 2 points, then every point has to lie on a higher indifference curve, right? So that immediately means that my indifference curve has to be shaped like this. It cannot be shaped like that. Because then any point on this line wouldn't lie on a higher indifference curve, it would lie on a lower indifference curve. So that would violate the condition for quasi-concavity of the utility function.
Sir?
Yes.
Can it be a straight line?
Say that again?
Can it be a straight line?
Well, that depends on, yes, good question. That depends on whether we're assuming strict convexity of preferences or weak convexity of preferences, right? Both definitions were there on the slides. Uh, if the preferences are strictly concave, then the utility function will turn out to be strictly quasi-concave. So this inequality will not be a weak inequality, it will be a strict inequality. And in that case, we'll have a picture like this, right? But if you only assume weak convexity of preferences, then the weak inequality holds everywhere. And that means that in the extreme case, the indifference curve is allowed to be a straight line. If it's a straight line, then you average out two bundles. The average bundle will be only as good as x1 or x2, no, not strictly better, right? So a straight line indifference curve violates strict monotonicity, but it does not violate weak monotonicity. Sorry, it violates strict convexity, but does not violate weak convexity. Guys, please turn off your microphones. Put yourself on mute unless you're asking a question. Okay.
So sir, this is basically saying that the boundary of upper level set, if it's convex, would be convex.
Yes.
Okay.
So the axioms 4 and 5, does the axiom 4 imply the fifth one and vice versa?
No. Once again, if we wrote down 5 axioms and one of them implies the other, or a combination of them implies the other, then we are doing a really poor job. Okay? Then that axiom which is implied is superfluous. We shouldn't have bothered to write it down. We're not being economical. Yes? So the axioms are supposed to be, first of all, independent from each other. Okay? None of the axioms should be an implication of the other axioms, right? Cannot be derived from the other axioms. And secondly, they shouldn't contradict each other, right? So it shouldn't be the case that some of the axioms imply the opposite of one of the axioms. That will make the whole thing contradictory. In the other case, it will make the whole thing just bloated and unnecessary and superfluous. Yes. Interesting tidbit. Let me just very quickly give you the tidbit. If you look at Euclidean geometry, right? Euclid systematized geometry in ancient Greece. He started with he wrote down some axioms, the Euclidean axioms, and then various theorems like the Pythagoras theorem could be deduced from those axioms. And one of the axioms was the parallel postulate, basically that if you have a straight line and you have a point outside the straight line, you can draw one and only one line which is parallel. Through that point, you can draw only one and only one line which is parallel to your starting straight line, right? So that's the parallel postulate of Euclid. And mathematicians for centuries debated whether the parallel postulate can be derived from the other axioms of Euclid, right? And for a long while, whether it deserves to be an independent axiom, that was a centuries-long debate, and eventually it was proved that it is not. It is indeed an independent axiom. You cannot derive it from the other axioms of Euclid. In fact, you can change the parallel postulate and you will still have a consistent geometrical. So those are called non-Euclidean geometries, where Euclid's parallel postulate is replaced by something else. Anyway, that's a digression. But in general, you don't want to write down superfluous axioms. You want it to be lean, right? And our 5 axioms have that quality.
So
yes.
So the diagram that you have drawn, can you just get it back?
Mm-hmm. Yeah.
So over there, what that diagram proves is the upper one. Can you just so second last one, this one. So this diagram proves that our preferences are convex, right? No, sorry, lower one, middle.
Okay.
Yes, this one, blue, this one.
Yeah.
So this diagram proves that our preferences are convex. How does it show that a utility function is quasi-concave?
No,
Because
this
if we will
diagram,
take averages of the two.
what I was discussing here, what I was trying to show or prove is that if the utility function is quasi-concave, then the indifference curves will be convex to the origin. That's what I was trying to prove. So I started by assuming that it's quasi-concave, and then I said that, okay, you know, that means that it has to look like the red curve, not the blue curve. So the argument, so the exercise here is to start by assuming that the utility function is quasi-concave and reach the conclusion that the indifference curves are convex. Right? You can also, I mean, you can prove all these connections. You can say, okay, if the utility function is quasi-concave, then preferences have to be convex. Right? That also follows from here, similar logic. But it's important to keep an eye on, you know, what exactly we are trying to prove in various segments. Here we are. There's no proof that the utility functions always have to be quasi-concave, right? We are talking of the logical connections between various assumptions. If we assume that the preference ordering is convex, then we can deduce that the utility function has to be quasi-concave. If we assume that the utility function is quasi-concave, we can derive that the indifference curves have to be convex and so
on. Excuse me, sir.
Yeah.
Sir, the quasi-convexity of a utility function and the convexity of ICs aren't actually the property of just well-behaved preferences.
Well, it depends by what you mean by well-behaved. I mean, you can make it a tautology. You can say that, well, yeah, I mean, well-behaved doesn't have any meaning in itself, right? If we define well-behaved to cover all the 5 axioms and not leave any out of it, then by definition, convexity is part of well-behaved. But you may want to define well-behaved in a more expansive way. You can say, no, anything which satisfies axioms 1 through 4, or maybe even 1 through 3 is well-behaved preferences. And we are looking at a more restricted class within that preferences. That's semantics. That's, you know, it depends on what you mean by well-behaved, right?
Okay, sir.
Okay. So getting back to the slides. Now, let's get down to business, really. You know, these are all sort of definitions and terms and some properties. So here's our consumer's problem. And as I said in a previous lecture, you know, the reason we have spent so much time and energy in proving the existence of a utility function, et cetera, is because the problem stated as a, stated in terms of preference orderings or rankings is a very unwieldy problem. We don't know how to sort of tease out a lot of theorems or results out of this kind of problem. And the big advantage of proving a so-called utility function capturing preferences is that the problem boils down to a simple constraint optimization exercise, right? Which is like this. Now, I'll kind of quickly get through this slide. I won't specify every detail. You can look at it and you can ask me, you know, if something makes you stumble. But the basic bottom line is that, you know, the most general formulation of the problem is maximize utility subject to a budget constraint, which is a weak inequality, right? You are allowed to throw away some of your money, and non-negativity constraints on the quantities, okay? Now, it's very easy to see that since the utility function satisfies strict monotonicity, if you increase the quantity of some good without decreasing the quantity of others, that means utility is strictly higher, which immediately implies that, this at the optimum point, this inequality will always bind, right? So we might just as well replace the inequality by an equality constraint, y minus px equal to 0, and that will not change the solution. Yes. Now, sometimes we may get a solution where some of the quantities turn out to be negative, and then that cannot be a valid solution. That will violate these things. So one way to approach the problem is to temporarily drop these inequality constraints, right? Replace this inequality constraint by an equality budget constraint, right? And then try to solve the problem. Okay. If the solution is such that the optimum quantities all turn out to be non-negative, then these constraints really have no teeth. You can bring those constraints into the problem, the nature of the solution will not change, right? However, if we find that for now we'll try to solve this problem, right? Maximize utility is subject to just a simple budget constraint, which is an equality, not an inequality. When we try to do that, if we find some of the quantities to be negative, then we have to be mindful of these constraints, right? And if none of the quantities turn out to be strictly negative, then we are fine. Then that's the true solution, even if you bring in the ignored constraints. Anyway, that's a bit of a sort of nitty-gritty detail. But let me move on to the main case, really, and we'll worry about some special cases. So here we have to apply Lagrange's method, right? The Lagrangian method of trying to solve constrained optimization problems. And again, you will get into the mathematical foundations of this in the maths course, if you haven't already. But let me just summarize in a kind of a recipe book manner. So in general, not just for this problem, in general, if you have a problem like this, okay, we are maximizing some function fx, which can be called the objective function, subject to a bunch of constraints, m different constraints, right? And each constraint will write in this manner that some function takes the value 0. You can write any constraint always in this manner by taking everything to the left-hand side and leaving 0 on the right-hand side, right? It can always be written like that. So whatever is on the left-hand side will be called the constraint function. Yes. So maximize some objective function, some subject to some constraint functions taking the value 0. That's a problem. Okay. What is Lagrange's method? Lagrange's method is really a mathematical theorem proved by the great mathematician Lagrange a long time back. We will not try to replicate his proof here. We'll just take the lesson. We'll just take it off the shelf. It says the following, that the gist of it is, speaking slightly loosely, that this constrained optimization problem, the solution to this can be found by thinking of, in some sense, an unconstrained optimization problem, right? Where we create a new function called the Lagrangian function. Now, what is this Lagrangian function? The Lagrangian function is, first of all, the objective function, the function that we're trying to maximize in the first place, plus some linear combination of the constraint functions, right? Each constraint function is multiplied by some new variable we introduce called the Lagrangian multiplier, and then all of that is added up, okay? So if you pretend that instead of trying to solve this problem, we are trying to find critical points, of this Lagrangian function. What are critical points? These are critical points at points where the first derivatives of this function with respect to the x's, the original choice variables, and with respect to the lambdas, the Lagrangian multipliers, right? The point at which all these derivatives of the function with respect to the x's and the lambdas is equal to 0, right? That's the critical point of the Lagrangian function. So maxima are characterized as critical points, minima are characterized as critical points. So it's as if we are trying to maximize or minimize this Lagrangian function. So so Lagrange proved something very, very useful a long time ago. He said, okay, find the critical point of the Lagrangian function with a little bit of qualifier. You have to check a second order condition, right? But putting that aside, the critical point of the Lagrangian function is typically the solution to the original problem that we were trying to solve, the original constrained maximization problem. That is Lagrange's theorem. Yes. It's absolutely, we have to be forever grateful to Lagrange for giving us this nice method of solution. Yeah. The meaning of what I said clear to everyone? You have a constrained maximization problem with equality constraints. You set up the Lagrangian function where you have introduced these new variables, the Lagrangian multipliers. And it is as if you're maximizing or minimizing this function. You set all the derivatives equal to 0 and solve. Right? That'll give you the solution. Okay, so let's apply that general mathematical technique to our consumer's problem. Yeah, this is our consumer's problem. Maximize utility subject to the budget constraint. We have one constraint only, but this technique allows us to handle more than one constraints. Forget about this. We'll just set the derivatives of the Lagrangian function equal to 0. Okay. So when you differentiate with respect to xi, you pick up a marginal utility, the ith marginal utility from this part of the Lagrangian. And then if you look at the other part, that's fairly simple. For xi, you have the coefficient pi and the coefficient lambda. So that's where this comes in, right? So this has to be equal to 0. And then the derivative with respect to the Lagrangian multiplier also has to be 0, right? And so if you differentiate with respect to lambda, you just get the stuff in the brackets equal to 0. And basically the derivative with respect to lambda is, as you can see, it guarantees that the budget constraint will be satisfied, but the constraint will be satisfied, right? That property essentially guarantees that we are not moving away from the constraint. Yes. Okay.
So why do we have a min lambda there in the Lagrangian?
For now, just stick to what I said, right? At this point, let me not get into that. The statement of Lagrange's method that I just gave you is that the solution, subject to checking some second order condition and all, will be given by the point where all the first derivatives of the Lagrangian are 0. Okay.
Yes, sir.
So let's adopt that from our math books. Now, this equation, and mind you, this is not a single equation, right? This is basically n equations. We are being pithy with our the way we are writing down things, because there's I takes the value 1 to n. So this is really n equations, and this is the n plus 1 equation. And we have n plus 1 unknowns, the xi's and the multiplier lambda. I put a star here because it's the value of lambda, and lambda and xi's, which make all these equations simultaneously true. These are the solution values. So the problem is that we don't want lambda star sitting here. Lambda is has done its job, and we now want lambda to go away. So is there a way, starting from these equations, to eliminate lambda? Well, there's an easy way. Take this to the other side, right? So marginal utility of the ith good is equal to lambda star, the multiplier, times pi, the price of the ith good. The same will hold true for the jth good. So if I write two equations, one for the ith good and the second for the jth good, and if I divide the left-hand side and the right-hand side, I can still maintain the equality, right? And when you divide the lambda times pi by lambda times pj, the lambdas cancel out. So that gives us this alternative way of writing down the first set of n equations, right? And now that has a very nice interpretation, okay? This is the ratio of the marginal utilities of good I and good J. Yes. We already saw in the two variable case, I made the derivation, but you can extend it to the n good case, that this is precisely the marginal rate of substitution between good I and good J, right? Or in other words, it's the slope of the indifference curve in the ijth plane, okay? This is the rate at which, in other words, in plain English, this is the rate at which the consumer is willing to substitute good I for good J, right? So if a consumer is choosing correctly and smartly, then the principle which describes the correct optimum choice, that principle says that the marginal rate of substitution between good I and J has to equal the price ratio. Okay. Now, what is an interpretation of the price ratio? How can we think of the price ratio in more intuitive terms? In the two good case,
Slope of the budget constraint.
so think exactly. So P1 x1 plus P2 x2 equal to some given y, right? So if I express x2 as a function of x1, I get it's y divided by P2 minus P1 by P2 times x1, right? So this is the intercept term.
So it is mainly the trade-off between the two goods.
Right. So the slope of the budget line is P1 by P2. All right. Okay. So our optimizing principle says that, and this we have derived mathematically, that at the optimum point, the marginal rate of substitutions equals the price ratio, and the price ratio is the slope of the budget line, again, on that ijth plane. Now, you know the pictures, right? So let's form up something, right? The principle of optimum choice for a consumer will understand it with pictures, with our more powerful mathematical methods, Lagrangian, and intuitively. And we'll satisfy ourselves that each way of understanding is the same, right? We are talking of the same idea, the same concept, once in terms of diagrams, another times sort of intuitive logic, and the third approach is the most general, powerful mathematical technique. So we have derived it in terms of the maths, you know, in full generality. Let's connect it to the diagram and the intuition. Okay. So in the diagram, and this you study, you know, it's bread and butter in microeconomics and basic microeconomics. So here's our budget line, and suppose, you know, the question the consumer faces is which point on the budget line should she choose? And suppose, as an example, she chooses this point, right? Do we know this point is the optimum choice? Well, to know that, it will be very helpful if we could draw the indifference curve through this point. So let's do that. And suppose it looks like this, okay? Here, this original point is not an optimum choice. Why is that? Because straight away in the picture, you can see that there are better choices. Look at any point on this arc, right? Any part of the straight of the budget line which lies above your indifference curve. Any such point is superior to this, according to these consumers' preferences. So let's move to one such point. Say move to this. We have moved to a higher indifference curve. But we are not finished. Even this choice is not optimum. It's better than the previous one, but it's not optimum, because there's still a part of the line segment of the budget line which lies above this indifference curve. So we can move to any point there. So we can keep doing it, and obviously we can keep improving till we reach a point where the indifference curve is tangent to the budget line. Okay, so if you think in terms of diagrams or pictures, you reach the conclusion that the optimum point creates a tangency between the indifference curve and the budget line. Okay. Now, why is that exactly what we saw in the maths? Well, what is the slope of the indifference curve? It's the marginal rate of substitution. It's the ratio of marginal utilities. What is the slope of the budget line? It's the price ratio. Okay. So this tangency condition that we have just discovered also means that the marginal rate of substitution has to equal the price ratio or the slope of the budget line. When you draw pictures, it's difficult to extend the logic beyond two goods, because it becomes difficult to draw the picture. That's the advantage of the maths, right? The math says that this condition should hold for every pair of commodities. So that's the generalization. That's the sort of more powerful extension of this little tangency condition that we can prove with the mathematics. Now, all of this would be somewhat ill-digested if we didn't talk about the intuition, right? So what's the basic intuition here? What's the intuition embedded in this equation of optimality? Anyone want to sort of take a stab at that?
So it basically
Only
means
relative price matters.
so it means that our psychological ratio of sacrifice is equal to the market's ratio of sacrifice.
Right. So what is the marginal rate of substitution? It's the rate at which the consumer is willing to give up one good for another. So if these are apples and oranges, if MRS is 3 and say oranges is on the vertical axis, then that means that she's willing to give up one apple if we give her 3 oranges in return. That's her willingness to substitute. What is the price ratio or the slope of the budget line? It's the rate at which the market is willing to substitute one good for the other, right? So suppose MRS is 3 and price ratio is 4. So that means in exchange for an apple, our consumer is willing to accept 3 oranges, but the market is willing to give him 4 oranges. So obviously that trade is profitable. So he'll move away from where he sits. So anytime there's no equality, he will want to give up one of the goods for the other good till this equality is achieved, right? And that's the intuition. The consumer doesn't want to trade or exchange stuff only when she reaches a point where the rate at which she's willing to give up one good for another exactly matches the rate at which the market is willing to do that substitution. Otherwise, she has not optimized. Otherwise, there's room for improvement.
So perhaps it can also be looked as that the unit change in utility per unit expended on one of the goods is equal to the unit change in utility per unit price for the other good.
Yes, except that, remember what was the starting point of ordinal choice theory? That we didn't want to talk about utility. Yes. We also, in our representation theorems, we proved that there's no one utility function. If you have a certain preference ordering, it can be captured by many utility functions, right? You can start with a utility function. You can take a positive monotone transformation. That will also give you a valid utility function. So marginal utility in absolute terms is difficult to interpret here. You take a log transformation of utility, your marginal utility to ith good will change, right? So that's, however, you can make a log transformation of your utility function. The marginal rate of substitution is not going to change. So take any valid utility function, MRS is always the same, although the individual marginal utilities are moving around, right? So that's why we don't want to formulate our intuition and understanding in terms of the absolute marginal utilities. We want to understand things in terms of ratios of marginal utilities, which remains preserved if you change the utility, if you move from one valid utility function to another. Yeah, this is a property of modern ordinal choice theory, not the classical kind of cardinal choice theory of Marshall, where Marshall assumed that absolute utility has some meaning, has some sense.
Sir,
Yes.
what is the significance of the value lambda which we are taking?
Well, let me not get into the details of that, but you can show that it essentially becomes the marginal utility of money. So if you increase income, consumers' income a little bit, I think that's what lambda becomes. At this point, we don't really need lambda. We have kind of used it and we have thrown it away. It's a device which helps us formulate the optimality principle in terms of the economic variables, right? Economically meaningful magnitudes like marginal rate of substitution, price ratio, etc. Yes, these things are well defined. We can observe the price ratio from the market. And in principle, we can observe MRS by, for example, taking consumer surveys, right? But even in principle, how will you measure lambda? So it's just a device. So let's not pay too much attention to it. Yeah.
Okay, sir.
Sir,
Yes.
Sir, it's a very small question, but sir, what if the good that we are considering, for example, good one and good two, what if they are not goods, they are bad, say marginal utilities are negative. Both of their marginal utilities are negative.
Yeah. If both are bads,
Does this
or even some are bads.
still work?
Yes. So if some are bads, if any of these things is a bad, that's not really a problem because you can define something else as a good. So suppose good I is bad, that means higher quantity of xi leads to lower utility. I can always define a new variable which is some number minus xi, right? So I can define some new commodity whose quantity is measured as yi equal to some big number m minus xi, right? So when you increase xi, yi actually goes down. So then with this redefinition, the good becomes a bad, right? So think of pollution, the amount of PM 2.5 in the air. Now that's a bad. We don't want it to be higher. We want it to be lower, right? But you can always define that. You can always redefine things where you say, okay, take some sort of absolutely high level of PM 2.5, right? 500 units, 500 micrograms per. So define a new variable which is 500 minus the actual measure of PM 2.5. So that new variable will be a good. So if you lower PM 2.5, the gap between that upper bar and the PM 2.5 measure goes up. So think of that new variable as a measure of cleanliness, not a measure of pollution. So if pollution is a bad, clean air is a good. Yes. The problem, we'll have a slightly different, we'll have some departure when something is a good for some range of quantities and bad for some range of quantities, right? Then there's no way by redefining variables, we will not be able to satisfy the monotonicity axiom. That's the case which is truly substantively different from our five axioms. Okay? Yes.
Could you please explain the process of how the consumer shifts between the goods if the MRS is not equal to the price rate?
So take a very simple, let me just use some numbers, right? So suppose the consumer has chosen a point, right? And goods I and J are apples and oranges, right? J is orange, I is apple, dx2, dx1. Yes, the second good is orange. The first good is apple. So what is MRS? So suppose MRS is 3 and price ratio is 4. What does that mean, right? In very intuitive terms. That means that the consumer will be happy to give up an apple if you give her 3 oranges, right? Whereas the price ratio of 4 means that the market is willing to give you 4 oranges if you sell an apple on the market. With that money, you can buy 4 oranges. Yes. So to give up an apple, you'll settle for 3 oranges, but you look at the market situation, you find that, well, you can trade that apple for 4 oranges in the market. So you will, as a consumer, you will make that trade. You'll sell an apple and you'll buy 4 oranges and you're happier. So whenever
Thank you, sir. Got it.
There's no equality, then the consumer can always adjust, can always do a little bit of trading, give up one good for another and improve her utility. All right. Okay, now, I think I'm not doing very well on time. But, okay, some cautionary notes, right? In general, this condition, MRS equals price ratio, will give us the true optimum, but not always. Okay, so there will be some exceptions which you have to be mindful of. So sometimes, as we have seen in simple problems, these are first order conditions. This MRS equals price ratio is a first order condition. Sometimes it will describe a minimum rather than a maximum, right? So we may be making a horrendous mistake if we solve for it and say, present that as the optimum choice for the consumer. It may be very much the opposite. It will turn out that if all the 5 axioms we have made hold, then we don't really have to, in particular, if strict convexity holds, then we don't have to worry about the second order condition. It will, wherever you have this tangency condition satisfied, it can only be a maximum. It won't be a minimum. I'll talk about that. So in general, we have to check second order conditions, but under strict convexity assumptions, we can ignore it. Yeah. Other possible problems that may arise are, sometimes the tangency gives us a local maximum rather than a global maximum, etc. And sometimes we have corner solutions, and that's something which we really have to keep our eye on, and it's a favorite in exams. So from a practical point of view. Okay, let me talk quickly about what I mean by these qualifiers. I think one of the problems in your problem set um, asks you to look at a utility function of the form x1 squared plus x2 squared. Yes? Now here you can apply your, first order condition. U1 by U2 is equal to x1 by x2, right? And that is equal to P1 by P2. Yes? So that would be one equation. And the second equation would be P1x1 plus P2x2 equals Y, the equation of the budget line, right? And you can solve, you have two unknowns, x1, x2, you can solve and find their values. That'll be the optimum choices. But that'll be wrong. So why is that? This utility function. Yes?
These are concave preferences.
Yes. This is the equation x1 squared plus x2 squared equal to some constant, right? That's the equation of an indifference curve. That's the equation of a circle, isn't it? With a center of 0, right? So the indifference curves are concave, not convex. Right? So if you choose the point of tangency, move away to any other point. If you're choosing A, you choose any other point like B, you have moved to a higher indifference curve, not a lower indifference curve, right? So A minimizes utility on the budget line, doesn't maximize it.
So,
yes.
So can you give an example like when can the preferences be concave in terms of goods, example in terms of goods basically?
Okay, so tell me what you mean by an example. Mathematical example, intuitive example, which will kind of, which will sort of say ring true.
So basically concave preferences means that averages are not preferred to extremes. So like when can that happen?
No, that's what I'm asking. What do you mean by when, right? Okay, let me go back to the intuitive interpretation of the convexity axiom that I gave you. That in some sense, loosely speaking, the precise definition is what we had. Loosely speaking, it captures some sort of preference for diversity. That was our interpretation, right? I gave you examples that, you have two, you have one bundle which is 2 cakes, another bundle which is 2 scoops of ice cream, and I create a third bundle which is 1 cake and 1 scoop of ice cream. You'll often want to choose maybe between the 2 cakes and the 2 ice creams, you say, oh, I don't care, right? But when I combine them, your eyes light up. You say, oh, this is a nice combo. I'll get this instead of just cake or just ice cream. So there's a preference for diversity. That was the interpretation. So if indifference curves are concave, that means the preference for diversity is being violated. So this is a consumer who likes to specialize, right? Instead of this kind of mix and match and, this assortment of various things, various kinds of nuts, this consumer says, oh, I don't want this, kind of Haldiram's box of some cashews, some walnuts, some peanuts. I'm not getting, I'll buy one whole box of peanuts and that's better. So it's a preference for anti-diversity. That's what this sort of indifference curve would capture. Does that answer your question? So people have various kinds of mindsets, right? So it's possible that some people, instead of diversity, they like one thing and always go for one thing. But anyway, coming back to the.
Yes, I like Gurava, but they mixed with dry fruits.
Sorry?
So that was by mistake from someone. You unmuted.
Okay, let me move ahead because I'm running out of time. So I want to not keep this thing hanging. So in this case, the tangency point is obviously. So what will be the solution in this case, in this picture, with this sort of utility function?
The extreme point, so
Corner
why
solution.
Corner solution.
corner
Given the budget
solutions?
constraint.
It'll be one of the corners. Yes, because anytime you move away towards the corner, you move to a higher indifference curve. So you'll either want to go and settle here, C, or you'll want to go and settle there, here, D. Now, which corner is the optimum choice? That will depend on details, price ratios, etc. We'll come to that. I'm not going to fully solve it right now. Well, maybe I will. So,
So,
yes.
so this concave indifference curve can also be a case where both the goods are bads, right?
If both the goods are bad, see, if both the goods are bad, that would just mean that the indifference curves are downward sloping per se, right? And if preferences are convex in the bad, then it'll be concave in the good, right? And if it's concave in the good, then it'll be convex in the bad. So to do the main kind of analysis that we are doing, if both are bads, we'll say after redefining the variables, converting them into goods, we want convex preferences. We want indifference curves to, in the space of goods, to be nice convex ones rather than concave ones.
So what I'm saying is that if both the goods are bad, then we can get a IC which is shaped like this, just like the concave shaped IC we have on the screen right
Sorry, there's a lot of disturbance. I didn't hear you well.
now. I think we are disturbing of someone.
Can everybody please mute yourself except for the
Sonam.
Yeah, Sonam. You were asking? Can you please repeat the question?
So what I was saying is that if both the goods are bad, in that case we'll get an IC which is concave shaped, just like the one we have on the screen right now.
No, if both the goods are bad, it depends, right? I mean, there's nothing written in the laws of nature which says that. The convexity of preferences is an axiom. It's an assumption we are making, and this assumption may be violated by some consumers. Yes. So even in the bad case, it can look like this, it can look the other way. It depends on what are we prepared to assume when it's all bads. Yes. Anyway, let me just say that, okay, this is something to be aware of, right? So you have to check second order conditions. But as you can see, if our fifth axiom strict convexity is satisfied, then any point of tangents, then that means these indifference curves are convex, and that means at the point of tangency you do have a maximum. Right? Sometimes, and many of these caveats arise when strict convexity is not satisfied. So you can have a case like this. Here's my budget line. And suppose the indifference curves are really, really ugly looking. They have convex parts, concave parts. So you can have, maybe it looks like this. Yes, sorry, I didn't mean to have an upward sloping part. So it's downward sloping, but it's convex somewhere, concave some other places. So this is a point of tangency. Yes. And if you have found it, you may be tempted to say, okay, this is the optimum choice. But look at the picture, A is as good as B here, but you can move from B to C, another point of tangency somewhere else, which is strictly better, right? In other words, you can have multiple points of tangency on the budget line. And then you have to compare them and choose the one which gives higher utility. Yes. So there could be a problem of uniqueness. But once again, notice that, this non-uniqueness problem arises when indifference curves are not strictly convex, when they have convex as well as concave parts. So again, if strict convexity is satisfied, we don't have to worry about non-uniqueness. But the thorniest problem is the case where we have a corner solution, right? So let's think of this. Let's try to solve this problem. Maximize x1 squared plus x2 squared subject to p1 x1 plus p2 x2 equal to y. Yes. Clearly, when is this corner? This is corner A, this is corner B. When is A the optimum choice? From the picture. Suppose the indifference curve through B is like this, right? Then the indifference curve through A will be a higher indifference curve. So here A is the optimum choice. Yes. But suppose it looks the other way around. The indifference curve through A goes like this, right? It lies below the budget line entirely. And then the other corner will be the optimal choice. The B will be the optimal choice because it represents a higher indifference curve, right? So what's the critical property in this case, right? A is the optimum, right? The optimum, the condition that you see is that the slope or MRS between good 2 and good 1 is less than the price ratio, right? So that means even at this point, the consumer wants to go in this direction, right? Wants to give up good X1, good 1 for good 2, right? But she's not able to because she has already given up all of good 1. There's nothing else to give up. That's why she's stuck in this corner. Over here, the critical condition which is satisfied at the optimum point B is that MRS is greater than P1 by P2. That's why she wants to give up good 2 for good 1, but there's nothing to give up because she's already exhausted. She has already gotten rid of all amount of good 2. She's only has good 1. So now, if we apply that to this exercise, x1 squared, so our MRS we calculated a moment ago is x1 by x2, right? So if x1 by x2 is strictly less than p1 by p2, then we have this corner solution, A. That means what? What are the optimum choices? x1 star equals 0, right? And what is the value of x2 star?
Y by P2.
That means all the money is being spent on good 2, so y by P2. And so here's a sort of neat way to write it. What are the demands or optimal choices? It's this: if x1 by x2 is less than p1 by p2, right? If the inequality is the other way around, if x1 by x2 is strictly greater than p1 by p2, then it's the other corner, right? Which means that x2 star equal to 0. And x1 star is y by p1, right? You're spending all the income on good 1. And there's, of course, one case where, x1 by x2 equals p1 by p2. In that case, both the corners are optimal. So this choice and this choice are equally good in that last case.
Sir,
Yes.
Sir, when we are comparing MRS and the price ratio, sir, what value of X1 and X2 shall we put so that we can compare the MRS and price ratio?
So the condition always is specific to a point, right? So when you have this interior solution, right, where the true solution involves both being positive, there the MRS equals price ratio condition actually helps you solve for the point where that is true, right? It gives you a bunch of equations, you solve it, you find exactly the point of tangency that way. Now, when you have a corner solution, you have these inequalities. You have these inequalities to be satisfied. If this is the corner solution, if this corner is the true solution, then this inequality better be satisfied at that point, right? How do you check? Well, put these values over here for x1, x2, and check whether that's indeed less than p1 by p2, right?
Yes, sir.
When you use these values, if you don't find this inequality satisfied, that means this is not a true corner solution. This corner is not the solution. And similarly to the other corner.
Okay, sir. Yes, sir.
Yes. So you check the inequality at that particular point on which we are focusing. Right. Now, in full glory, these conditions are called Kuhn-Tucker conditions. In maths, you will kind of, go into much more detail and you will see it in full detail. In many problems, you have two goods, you don't have to sort of formally write down Kuhn-Tucker conditions. You can use the kind of intuitive logic that I just used, right? If the solution happens to be at a corner, you have to check whether, if it's an upper corner, this relationship between MRS and price ratio has to hold. If it's at a lower corner, this relationship has to hold. So for each corner, just check whether the relevant inequality holds. And if it does, that corner is a solution.
Sir, so we do not need to necessarily show the mathematics behind all the solutions if we give the proper logics like this.
You don't have to show the mathematics in the sense that you don't have to formally write down the Kuhn-Tucker conditions, right? But if you use a logical argument to like the way I've used it, using diagrams and slopes and inequalities, then that's fine.
So the Lagrangian is not necessary, but we need to justify it properly.
Yeah, so, okay. Very quickly, way over time. Oh God. I'll just end with this last bit. Yes. Just 1 second, okay? This is a famous Cobb-Douglas utility function, right? So suppose we are maximizing this subject to P1x1 plus P2x2 equals y. Now, if you stare at this problem, and especially the utility function for a little while, you will immediately realize that the optimal solution can never be at the corner. You will never choose so that consumption of one of the goods is zero. Why is that?
Then utility would be zero.
Utility would be zero, but that's not the end of it, right? Zero utility doesn't have any meaning in itself. But if I'm choosing, if one of the goods has zero quantity, then utility is zero. And if I choose any positive combination of the goods, anything, I get a positive value of the utility function. So that means that compared to any corner point or point on one of the axes, any interior point is better. Okay, so if you draw the indifference curves of the Cobb-Douglas utility function, they basically, those indifference curves never touch the axes, right? They are asymptotic to the axes. So if your budget line is like this, and if you have chosen the corner point A, choose any other point on the budget line, it will take you to a higher indifference curve, right? So in this kind of a problem, right at the outset, just by inspection through the kind of logic that I just gave, you could say, okay, you know, this problem won't have a corner solution, so I don't have to worry about it. So that means I have an interior solution, which means that, you know, the tangency condition will describe it. So then you proceed with setting up the Lagrangian, writing down the first order conditions and solving it.
Good afternoon, sir.
Yes.
Sir, I had a non-academic doubt about midterms.
Okay.
Sir, in our timetable, the schedule for midterms is 28th to 30th January. So, I mean, will it happen on those dates only? Like our syllabus is not, I mean, I saw through the slides. I mean, it's not like, will it happen? Will it happen in January end or?
I will finish before that. Yes.
Okay, so the dates would remain the same.
Assume that it's those dates.
Okay.
Right.
Yes, sir.
It won't happen before. If there's a, for some reason, because you know everything is a little uncertain this year. If for some reason it has to push back, then I'll let you know. But for now, assume that it's in that range.
Okay, sir. Thank you, sir.
Any quick questions? We are way over time.
Good afternoon, sir.
Yes.
So, could you explain in brief, like what exactly are Kuhn-Tucker conditions? Like, just summarize them in brief.
Kuhn-Tucker conditions. Okay. Again, I won't give you the full detail, of course, right? You'll cover that in maths. Okay. Let me kind of try to wrap our heads around it. So in the stuff that I've done today, I've, you know, in the Cobb-Douglas case, for example, right, the solution is going to be interior. And the solution can be obtained by solving that MRS equals price ratio condition. That will hold in this case, right? But then we saw other problems like, you know, where the utility function is of the circle form, where the solution is always at a corner. Yes. So when the solution is at a corner, the condition involves some inequality between MRS and price ratio. And when the solution is interior, it involves an equality between MRS and price ratio. Okay. Now,
yes, sir.
I can combine these two conditions and kind of write them down comprehensively. Right now I can write down and say, okay, for when the solution is interior, MRS equals price ratio. When it's in this corner, MRS has to be less than price ratio. When it's in that corner, MRS has to be greater than price ratio. So if I sort of pool all these cases together and describe them comprehensively, I have basically written down Kuhn-Tucker conditions.
Okay, sir. Understood, sir.
Yeah. Anything else?
Sir.
Sir.
Yes, go ahead.
So we can meet you during your office hours, right, tomorrow?
Tomorrow, yes. So I think I got some emails. I'm quite backlogged. Oh,
Yes, sir.
the video was off. I didn't realize that. Anyway,
Yes, sir. I think some of us emailed you to set up an appointment.
yes. So let me take your questions uh, in this through this very link, right?
Sir, I think we lost you for 5 seconds. Could you please say it again?
I'm saying that let's meet here. Whoever has questions, so we'll meet here. What was the time I gave? 2 to 3, right?
Let me check.
Oh, sir, there's just one quick question, sir.
Yes.
Sir, when we are comparing marginal rate of substitution